So let's solve the vehicle routing problem using the Clark-Wright savings algorithm. So the general approach is pretty interesting actually. So what we start with is a complete solution, an out and back solution. So in this simple example here, I've got one origin and 4 demand nodes. So I'm going to create 4 tours, one to each one. It's going to be loaded out and empty coming back. So then I want to identify potential nodes to link together. So let's look at this. I'm going to do this by calculating what's known as the savings equation. So the current solution for nodes 1 and 2, the current cost is 2 times the distance going from origin to 1, right? 1 going there loaded and 1 coming back unloaded, plus 2 times the cost of going from the origin to 2, right? Because I have to go and come back. So I have 2 out and backs, one to node 1, one to node 2. So that's my cost. What would my cost be if I joined nodes 1 and 2 into a single tour? Well, it would look something like this, the green arcs, and that would be the cost from 0 to 1, plus the cost from 1 to 2, plus the cost from 2 to the origin. So it makes sense to tie nodes 1 and 2 together in the same tour if the cost currently with the 2 out and backs is greater than the joined cost. That is, if those black costs are greater than the green costs. And if so, then I should join them together. We can simplify that equation by bringing all the terms from here, the right-hand side, bring them to the left side, and I get what is known as the savings equation. So the savings value is simply the cost from the origin, or the DC, to node 1, plus the cost from 2 to the origin, which is symmetric, origin to 2 or 2 to the origin, minus the cost in between. So if this value is greater than 0, then it makes sense to bring those 2 nodes together. So what we're going to do in the algorithm, we're going to calculate the savings value, and then I'm going to sort them from highest to lowest, and then I want to run through and join those nodes that save me the most money first. Now we need to make sure of a couple things. When I add 2 nodes together, I want to make sure that I'm not exceeding my vehicle capacity or some other violation. Also, when we have tours of more than 2 drop-offs, so I have 3, then I want to have an interior node. So if there's a node that's in between 2 other demand nodes, I can't connect that with another node to see if it fits into another tour. I'll show that in our example, but it has to be an end node, something that's already going to or coming from the origin or the DC. All right, so here is our situation. It's the same problem we solved for the sweep algorithm. I've got 10 demand nodes in a DC. Each vehicle, I've got 4 of them, has a capacity of 200 units. And so here's the savings heuristic, kind of how I described it. And what we do first is we calculate the savings matrix. Now what I showed in this table is actually 2 things. The top half in the orangish color is actually the distance matrix. Remember how we talked earlier that it's symmetric? I don't need to show both halves because the distance from, say, node 3 to node 5 is the same as going from node 5 to node 3. I only need to show that half. This allows me to use the bottom half for the savings. So how am I calculating the savings? Well, let's pick one. Let's pick node 1 and node 9. What is the savings if I join those together? Well, using our savings equation, it's the cost from origin to 1, that's 7.1, plus the origin to 9, that's 5, minus the distance of 1 to 9, that's the 6.4. So that gives me 5.7. And so what I put here in the little blue colored part of the matrix, combining 9 and 1, the savings is 5.7. So you can calculate this very quickly in a spreadsheet. And so this is how you create this matrix. So the top half is the distance, the bottom half is the savings matrix. So the next step is I take all those savings and I sort them. And so what I did is I put them into a column. So on the far right table, I've got the arc ij, and then I've sorted from highest to lowest. So combining 7 and 6, let me just circle it down here in the savings matrix, is 13.8. That's my most savings. The pairing I and J together, 6 and 7, saves me the most. So that's where I'm going to start. Okay, so let's go to our problem. And this is the same problem we've been working on. And so the first solution is find the total distance. So I'm doing the out and backs to every one of the nodes. And that total tour distance for all the 10 tours is 133.2 miles. And I'm pretty sure we can do better than that. So now I'm going to start with the first arc. I'm going to see if I can join nodes 6 and 7. This is the top one on my list. So joining them together, I see that by having the two loads, 80 and 78, does not exceed my 200 unit capacity. So I do it. So now I've replaced the two out and backs with one large tour. I saved 13.8 miles, so my total tour distance has now gone down to 119.4. What do I do next? I go to the next one on the list, arcs 10 and 9. That's going to save me 10 miles if I can put them together. So let's consider it. I look and make sure capacity is not violated. 85 and 42, the demand for each of those is less than 200, so I'm okay. So I'm going to join those, and I've got one tour going from the DC to 10 to 9 and then back to the DC. Next, I'm going to look at combining nodes 4 and 1, because that's the next one on my list for a savings of 9.3. And again, I look at the capacities and the demands, and it seems to be fine, so I'm going to add that together. And now the next one is 4 and 3. So now, because 4 is an end node, it's not an interior node, I can consider adding that. And I compare the capacity. So the vehicle going from 1 and 4 had a capacity of had a load of 76, and I'm adding on for node 3, 53 more units, total of 129, still less than the 200 capacity, so I'm good to go. So now what I've got here is a tour from the DC to 1 to 4 to 3 and back to the DC. So when I was talking earlier about an interior node, that's like node 4 here. So I can't pair node 4 using the Clark-Wright algorithm to any other node now because it's interior. I can only consider the end nodes of a tour. Okay, so let's keep going. I've got working down my list, and my next one up is combining nodes 10 and 7. So I look at that. Now, the 7, that means I would have a current load of 127, and I'm combining with a load of a demand of 158. So that exceeds my 200. I cannot combine those two because that would have been a tour from the DC to 6 to 7 to 10 to 9 and back to the DC. The truck isn't that big, so I can't do that. So then I go to the next one on the list, combining 10 and 1. And again, I see that the capacity is exceeded there, so I skip that one. I go to the next one, nodes 5 and 3. So that one can be added. 3 is an end node on the tour. It's not interior. So I can add that, check the capacity. I'm adding 31. It was at 129, so that's good to go. So I add that one, and that replaces, so I'm turning into a rather large tour down there. So the next one I want to consider is 6 to 5. I look at that, and I consider how much more load would be put on, and it violates the capacity. So I can't do that one. So now I look at the next one on the list is 7 and 5. See that one? Again, it exceeds the capacity, so I can't do that. Next one on the list, 5 to 2. So that one works. That gives me a total load of 178, so that's fine. So that gives me one big tour that's going to go from DC to 1 to 4 to 3 to 5 to 2 and back to the DC. So at this point, I know I'm done because I've got the vehicles. The only other tours that could be combined would be loading in with load 8. But you see that load 8 has a demand of 84. So I know that can't be combined with any of the vehicles because it would exceed the 200. The algorithm would still go through considering all of these arcs and for combining, but we know we can stop now. So our final solution will look something like this. So we end up with 4 routes. So I labeled them the blue route, the red route, the orange route, and the green route. And each one of these would be a vehicle. Now, once I clustered, you notice the nice thing is it's kind of determining our sequence. So it's a pretty nice algorithm. It does something else that's pretty neat. And when we were pairing two nodes together, I checked whether one, was it an interior node or not, and two, did it exceed capacity. This algorithm is well suited to handle other considerations. Let's say it's a hazardous material and certain loads cannot be combined. During that check, to check capacity, you could check other things like can that type of vehicle serve that location? Can the goods from the two locations be combined? All those different things. So it has a nice built-in check that allows you to check to see if the pairing violates some other condition, not just capacity of the vehicle. So it's a really robust algorithm, and it's widely used because it's very fast and it's very efficient.